This video is designed to help you take a shorthand molecular structure like you see here and convert it into a longhand structure. And that's really important because you need to be able to identify every single bond in a molecule for this project. So first thing we're going to do is we're going to notice that this amino acid, which is tryptophan, which by the way is an excellent option for those of you choosing molecules, like any of the 20 amino acids are great. The sugars are great, the alcohols are great. If you want to challenge yourself, then you can choose some of the pigments or some of the drugs that are listed on there. But all the amino acids are great options. So tryptophan is C11H12N2O2. And the first thing you're going to notice is there's supposed to be 11 carbons, and I don't see any carbons in that shorthand version. So here's what organic chemists are doing. They're leaving them out to make life a little simpler on themselves. And so we are going to start off by adding in where all the carbons are. So everywhere there's a junction, there is a carbon there. Okay. Once we have added in all the carbons, the next thing you're going to notice is we're missing a lot of hydrogens. There's supposed to be 12 hydrogens, and I only see like 4. So where in the world are those going to go? We all know, hopefully by now, that carbons need 4 bonds. Uh-oh, that carbon only has 3. So we've got to give it a hydrogen. So you're going to go along and you are going to actually do that for every single carbon. You're going to double check it to make sure it has 4 bonds. So this carbon here has 1, 2, 3. Aha, it's going to also need an extra hydrogen there. An extra hydrogen there, an extra hydrogen there. Ooh, that carbon's lucky. It has all 4 already, so it's good to go. This carbon also has all 4. This carbon has 1, 2, also 4. Ooh, this carbon only has 2, so we're going to have to add 2 extra hydrogens there. This carbon needs an extra hydrogen. Again, you're just counting the lines coming off of it. That one already has 4. That one has 4. 4. Okay. Now forgive me, I'm going pretty fast, so there is a chance that I could be leaving something out. But go back and just double check all of your carbons, double check all of your hydrogens. They should each have 1 bond. Now let's kind of expand it the rest of the way. We're also missing some things like, for example, an oxygen hydrogen. Well, that's 2 atoms that are bonded together. So you should go in and add all of the bonds whenever they show a shorthand like that. So this is a nitrogen bonded to a hydrogen. All right, so and then what's the deal here? Good heavens, NH2. That means there's 2 hydrogens bonded there. So there's 1. Let's go ahead and draw in the other one. And then let me show you a trick. I suggest just changing your highlighter to, actually change your pen to white and make it maybe a little bit thicker, and then just color out that 2 once you've added it. So you have both the hydrogens showing like you've expanded the shorthand version, but you don't have that 2 hanging out there because that could be really, really confusing. Okay, now we have all of our bonds drawn. And we have all of our carbons, all of our hydrogens. You always want to go back and double check the formula up here to make sure it matches, to make sure everything's accurately represented. And then now let's go do step 2, where you highlight the polar bonds blue and the non-polar bonds yellow. Now I already made a video about this where I show you exactly how to determine what kind of bond you have. You might remember that it has to do with subtracting electronegativities. So take carbon and hydrogen, for example. The difference in electronegativity here is 0.4. And if you have an electronegativity difference of 0.4, then that is non-polar. And we know that because anything from 0 to 0.4 is non-polar. So that gets colored yellow. So everywhere you have a carbon-hydrogen bond. Now you also know that every time you have a carbon-carbon bond, 2.5 minus 2.5 is going to be 0. So all of the carbon-carbon bonds are also nonpolar. And nonpolar, remember, just means that the electrons are being shared pretty evenly. There's not a side of that bond that's a little bit more electronegative than the other. I mean, a little bit, but not big enough to really have like a really clear positive and negative side of that bond. So I'm going to go ahead and just show all the nonpolar areas. Where's all the nonpolar? Again, all of the carbon-carbon, all of the carbon-hydrogen. Now, this leaves some other curiosities, right? So nitrogen and hydrogen, you will notice that that is above 0.4. So now we are in the realm of the polar bonds. So this is showing you that there is one side of that bond that definitely has the electrons around it more often. Let's check carbon-nitrogen. Aha, that's a 0.5, so that's also polar. So we're going to go through and color all of the polar bonds. Don't forget these little guys that you put in here between oxygen and hydrogen and between nitrogen and hydrogen. And then let's see, carbon and oxygen. Yep, also polar. And then go back and double check yourself. You know, make sure every single line you have on here, with the exception of the double bonds, because those count as the same thing, is colored either blue or yellow. Ooh, and I forgot one right here. That's a kind of tricky one, right? It doesn't look like a bond, but it actually is. And that one is also polar. So once you have every single line with a blue or a yellow color, we can now go over here and count how many bonds we have of each type. So I'm going to change my color coding here. Hydrogen bonds, you might remember, are when a hydrogen is bonded to either a fluorine, an oxygen, or a nitrogen. That's the only way you can have H bonds. So let's see if we have any of that. And it doesn't hurt to like color code all of this so you can find out what's going on. So let's look for hydrogens. Aha, there's one. Hydrogen bonded to an O. Ooh, there's hydrogen bonded to an N, hydrogen bonded to an N. There's another hydrogen bonded to an N. Let's see if we have any others. All right, that's all I see. So 1, 2, 3, 4. So you'll put a 4 there. All your other blue bonds that you have left are automatically dipole-dipole because they are polar bonds that are not hydrogen bonds. So again, I really highly suggest the color coding thing. So we have 1, 2, 3, 4, 5. All right, looks like we have 5 dipole-dipoles. And again, forgive me, I'm going really fast, so I might be skipping something. Write me a note in the comments section if you can catch a mistake. Man, I would love that. All right, let's take a look at the final, the London dispersion. Those are all the yellow, the very non-polar bonds. These hardly hold other neighboring molecules to them. So we have, I think, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, I think we have 18. See how much patience this takes? This is like not for the faint of heart. There's a lot of work in this. So we have 18. Okay, now your molecular analysis is pretty close to done. You just have to write down like what is the greatest polar bond difference, which is just you going up here and finding out which one of these bonds is the highest electronegativity difference, and you'll record that there. Then polar functional groups. All right, so let's just try to figure this out. I have a whole bunch drawn out down here. So let's see what they look like. Sometimes they, oh, by the way, all of these are carbons. Carbon, 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 every little gray squiggle. So we can look for something called an amine, which is a carbon bonded to a nitrogen. We can look for an alcohol, an oxygen bonded to a hydrogen. Let's see, oh, there's aldehydes and ketones, esters. So let's go up and see if we have any like nitrogens, oxygens anywhere in our molecule. See if we can find any of these combinations. All right. Ooh. So nitrogens often like to form something called amines. So I'm going to go ahead and change to a highlighter color here. So we have a nitrogen bonded to a carbon right there, another nitrogen bonded to a carbon, an oxygen bonded to a hydrogen, a carbon bonded, double bonded to an oxygen. So again, you can even like circle them and then go down and be like, what are those? So what's a nitrogen bonded to a carbon? Is that anything? Oh, that's called an amine. Okay. So we'll go back up here, a nitrogen bonded to a carbon. It's called an amine. And then we have another amine right here. And you may have highlighted something that turns out not to have a match, and that's like perfectly fine. Then you just unhighlight it. Remember, this is yours. That's the beauty of notability. A carbon double bonded to an oxygen. Oh, because remember, this is a carbon here. So that has a name. That's called a ketone. So let's go up and find that carbon double bonded. Aha! Carbon double bonded to an oxygen is a ketone. This one has all sorts of functional groups. And this one over here is called an alcohol. Oops. So when I go to count the functional groups, I have 1, 2, 3, 4. And I'm just going to put 4 polar functional groups. Counting carbons is just a matter of looking up here. I should have 11. Double check yourself in the molecule. Should be able to count 11 C's there. 11. Okay. Then let's just take a look at one more thing that's really important for you to notice. Do you notice this copper right here? Hopefully you guys are starting to recognize that that is a metal. So magnesium is a metal, and calcium is a metal, and copper and gold and zinc, like they're out there, and sometimes you do have these ionic bonds. Remember, an ionic bond is between a metal and a non-metal. So that means I have to put a 2 right here, because there's 2 spots where that copper is attracted to the nitrogens. And so be very cautious of looking for any sort of metals in your chemicals as well. All right, hopefully this was a little bit helpful on how to expand the shorthand, be on the lookout for ionic bonds, and how to identify functional groups. Let me know if you want me to make another video.